So, we have been discussing about armature reaction in DC machine, and for that I took a generator mode of operation and assumed this direction of rotation and assumed that this pole is north pole and then this side is south pole. I am not showing the field winding. So, under no load condition, when armature is not carrying any current, then the lines of force will be uniformly distributed over a pole, that is the flux density will be same. But the moment armature is loaded, this side of the conductor all will carry cross current, all will carry cross current here, and this side of the conductor will carry dot current. Got the point. But the moment armature carries current, this there will be a concentration of lines of forces on the on this side. Up to half it will be something like this, and then it will be rarified here in this zone. Opposite thing will happen here, the lines of force will go concentrated, is not, because of this dot current, it is like this, and it will be rarified here. So, half of the pole will have more flux per pole, I mean more flux, and so there will be an increase in flux in one half and another. In this context, I will tell you just one very basic information all of us are having. Suppose you have a magnetic field, okay, and suppose it is carrying a current I in this direction. So, it is a suppose a uniform magnetic field. When it was not carrying current, it was uniform like this. Okay? When it was not carrying any current, that is fine, uniformly distributed. But the moment to this same conductor you pass a current I, the lines of force will be like this. Lines of force will be like this, and you can easily see the lines of force here will be more now after it carries current. So, lines of force will be thicker, thicker means concentrated here, because whatever lines of force was provided by the original field will be strengthened, and here it will be in the opposite direction, it was downwards, here lines of force will be rarified. That is what I am trying to tell. And another interesting thing is, if this is the picture, this is some current the conductor is carrying, and you just imagine that these lines of forces are elastic sort of thing. So, if you just pull them like this, then the conductor will experience a force this side, force. This is of course, I know from left hand rule, this is what is going to happen by applying left hand rule this way. Current B, and this is the direction of the force. That is, conductor will always move from high concentrated field to low concentrated field. In this case also same thing happens, that is, the electromagnetic torque will be in this direction, consistent with the prime mover torque, which has set the rotation. So, prime mover torque is also in this direction, electromagnetic torque will be like this. So, so this picture is like this, and the argument was, okay, in general for low value of armature current, increase in flux in one half and decrease in other, if they are equal, then flux per pole will remain same and nothing appreciable is going to happen. Also, you recall the direction of the torque can be also found out, I told you earlier, because of the interaction of the two fields of the armature and that of by the stator poles. In this case, this side of the iron of the armature will become N not pole, and this side will become armature poles will be NASA, and you can see this Na will be repelled by this N. The position of this Na and SA in case of DC machine is same, with time it does not change, it will not move because of commutator and brass arrangement, that is the beauty. In so many ways you can explain this armature reaction. Now, as I mentioned in my earlier lecture, that increase of flux in one half will really not be compensated by decrease in the other half. In fact, decrease will be less than the increase in one half. I mean, increase will be less than the decrease in the other half because of saturation effect. If that be the case, then the induced voltage will suffer a loss of voltage. So, now new flux per pole will be not by a very large amount, flux per pole will decrease, because after all in one half increasing, another half but decreasing, but only thing is this, the increase in the half where increment take place, that is slightly lesser because of saturation effect. There will be a net reduction in flux per pole. Some people what they do, they will simply say that okay, because of armature reaction flux is reduced by 4%. By that some problems may be set with experience, okay, flux per pole becomes, or you measured the generated voltage, try to estimate the generated voltage, and from that you see that effective reduction in flux per pole may be 2%, 3%, 4%. So, original flux was 5, it will then become 0.955, 5% decrease with respect to the no load field present in the machine. So, apart from the loss in voltage, there are other ill effects of armature reaction that I am telling you now, and these are much more problematic. You see that in the machine, I will redraw this, nothing wrong in redrawing, so that you understand better and better. This is the armature, it was there, okay, and there was the brushes, there were the brushes, and here are the conductors. Now, these points are important for DC machine, I mean very important. See, this was your poles, good. They are not permanent magnets in a practical DC machine, windings are there. Okay. Now, under no load condition, lines of force will cross the armature and reach the south pole, complete its path through the yoke portion of the iron of the stator. What will be the flux in this axis? So, this axis, at some times I mentioned this to be my direct axis, D axis, along which the stator field operates, and this axis some people call it Q axis, quadrature axis. When the armature is not carrying any current, what is the field? Here the field strength is how much? Okay, whatever is this. What will be the flux in this direction? 0. When IA is 0. No flux in the quadrature axis, in the Q axis, where brushes are placed. Therefore, no flux in the quadrature axis. However, when there will be armature current flowing, armature MMF, I do not want to, okay, let me disturb this. So, suppose these are carrying cross generator mode, this direction it is moving, and these are all cross. These are dot, nice, no problem. The moment you do this, the armature MMF effectively it is cross, it is dot. So, it will be like this way. So, that is why this fellow has become a North Pole on the rotor iron. So, lines of force will be like this, and this will be the armature MMF along the quadrature axis, which was hitherto absent when the machine was under no load condition, IA was 0, but now there appears a field here. Therefore, I would now expect there will be some flux per pole here, some flux B present here because of this armature MMF along the quadrature axis. And therefore, the coils, this coil, when it was under the influence of North Pole, its other coil side was under the influence of the South Pole, having cross dot currents. After they crosses this, comes under South Pole, they have to carry current in the opposite direction, and it is conditioned, you cannot do anything about that. The moment it crosses to this side from left to right, crossing the Q axis or brass axis, it has to carry this dot and cross current, it has to. When armature current was 0, but it has to pass through this zone Q axis. When armature current is present, when this coil will come here in the Q axis, it will also have induced voltage in it. With what polarity? It was under influence of North Pole. This is the armature MMF. So, still under the influence of another North Pole as if. This is the South Pole of armature, this is the North Pole of armature. So, flux lines it is coming like this. Therefore, it will still have cross voltage induced in it. Therefore, the switching of current from cross to dot will be delayed. I will explain that term in a much more simpler way, but before that you understand that okay, earlier it was like this cross under no load condition, it comes here, voltage becomes 0, current is 0, then you ask it to carry dot current. That was one thing. So, it was getting some time, current became 0, then became dot. But here it is almost when it is present here in the otherwise magnetic neutral zone, when I A was 0, this was the magnetic neutral zone. There was no induced voltage in this conductor, and but with armature current I find, oh, this is cross, this is dot, still it has to carry current. So, this process of changeover of current direction for a particular coil, each coil will undergo this process. After some time this fellow cross to dot current, it has to become. So, this process is called what is known as commutation, commutation of current. An important term in a DC machine, it has to. Achha, this is one thing, and another thing is which while explaining the DC machine armature winding, what I told is this. I will draw a very rough figure now. See, there were several coils, I drew like this. I will draw a few of them. It was like this, and there were commutator segment. Commutator segment I am now drawing bigger, okay, so that we understand the process. And there are so many commutator segments, and all coils are connected in series. Is not? And the coil ends are terminated these junctions on commutator segments. You recall that? Like that it went on. And there are brushes here. This side is under north pole, this starting, etc. So, brushes were here. Brush width is same as the commutator segment. While calculating the voltage per coil in the armature, I told you one thing, okay, it is running at a high speed, assume half of the coils it is expected, half of the coils is under north pole, half of the coils is under south pole, and based on that I calculated the armature voltage. But I did not tell that okay, there may be a situation one coil will be in the quadrature axis also at some times, it has to. But since the number of coils are more, to calculate the induced voltage it will not cause any problem. Suppose there are 100 coils, one coil will be undergoing such a process, one or two coils, when they will pass quadrature axis and go to that side. And interestingly, under no load condition, the coil which will undergo commutation, I will draw it what I want to say. There are two commutator segments. Brush width is same as the commutator segments width, and here is a coil on the quadrature axis. This is coil in quadrature axis. This is the brush. These are the commutator segments. insulated by mica insulation. And there are other coils here like that. It is under north pole, there is next coil that is under south pole and so on. But you see this coil is then it is the direction of rotation, this coil is now undergoing commutation. Earlier it was carrying some current this way, and after it crosses it will carry current in the opposite way, same current, but in the opposite direction. And I now find that this coil is undergoing commutation. When it is undergoing commutation, in the this coil you see it gets shorted. By whom? By the commutator segments, which is moving in space, but at that instant it will be shorted by this brass and this commutator segment and here. Under no load condition there was no induced voltage, no problem. But now when the armature current is more in the quadrature axis, it is not true that the flux is 0. There is some flux, some B is there. Therefore, BLB induced voltage there, and induced voltage will be there, and that induced voltage will circulate some short circuiting current. Not in the other coils, but only the coils which is undergoing commutation. But the boundary condition is when the coil was this side, it has to carry current I in this direction, and when it goes to that side, it has to carry current in this direction. That is the boundary condition, nothing doing. Now, therefore, it looks like there will be some problem. Problem means there will be some circulating current if there is flux in the quadrature axis, and also coil has to change the current from plus I to minus I. It has to change the current. In any case, this coil has also got some, however small it is, a small inductance associated with coil. Any coil is having some inductance which is proportional to n squared, etc. We know that. The period of time during which this commutation will take place is very small, because machine is running at a high speed, everything is happening very quickly. Therefore, if I say a coil having some inductance cell and the current is changed from plus I to minus I in a very less amount of time, do not we expect some induced voltage in the coil L di dt, which will be very large, because in a small time from one finite value of plus I to minus I it is changing. Therefore, there will be also induced voltage in the coil. What will be the polarity of the induced voltage? Polarity of the induced voltage will be such that it will try to oppose the very cause for which the voltage is due, that is, it will try to oppose the change of current. For smooth operation of DC machine, I would expect the changeover of current from plus I to minus I takes place very peacefully. Plus I, then it becomes 0 in the quadrature axis, then it becomes minus I. But inductance of the coil, which is short circuited, will prevent that. That is, the induced voltage in the coil is such that it will try to still carry plus I current, and that is why people say commutation is delayed. And not only that, there will be large induced voltage in the conductor, L di dt will be large, and this voltage may even, because it is a thin mica insulation, may cause a flash over between the commutator segments. See, there are so many things happening here. The coil which undergoes commutation gets short circuited in the quadrature axis. By whom? By the commutator segments and the brass in the quadrature axis. That is one aspect. There will be, we expect some circulating current, which I do not like, because current still persists, and the polarity of this induced voltage because of rotation of quadrature flux I just told in the previous diagram, it is same like this. It cannot distinguish, north pole it was under, still north pole under, and that is I am making a situation coil still carries plus I, although finally his task is he has to carry a minus I current, and minus I current it will do in any case, and the price we pay for that is the large induced voltage across the coil L d I dt. And that large voltage may puncture this, there may be a direct flashover between the brushes, and there will be arcing taking place between the brushes, flashes. It is a common practice. If you see a DC machine running, and if you can see the commutator segment moving at a high speed, there are brushes, and you switch up the light, you will find there are arcs between the commutator segments. It is because those coils which are undergoing change of current from plus I to minus I under a short circuitic environment like this, there may be a little flashover. That is why one disadvantage of DC machines is that it cannot, it is ruled out, you cannot make use of it inside a mine, for example. There may be explosive gases, and because of this flashover there will be fire, out of question DC machine, because it is bound to have some flashover between the commutator segment, even for normal operations. Apart from it may affect the your nearby communication network, it will radiate energy, all these things, because high speed it is running. If you have a radio set or TV on and nearby a DC machine is running, you will see that disturbance will be picked up by your TV set, picture will be spoiled, disturbed. So, all these things I am telling is that armature reaction has a far reaching consequences in terms of various things. It will delay the commutation, it will not make a smooth changeover of current, although plus I to minus I, the moment it crosses it has to carry minus I, and you are giving it a very small time, high speed it is running. Suddenly it was here, it goes there, large voltage will be induced, that may puncture the insulation, mica insulation, this is a thin mica insulation, and it may it will cause problem, and it cannot be used DC machines. This is the reason. In normal case also there will be a little bit of flashover, and you rule out the use of DC machines in a hazard environment with, I mean particularly mines, etc. DC machines cannot be used, conventional DC machines. Okay. So, these are the ill effects of armature reaction. For small machines, people do not care, okay, a little bit of flashover will take place between the brushes every time a coil undergoes commutation, say up to few kilowatts you tolerate it. but suppose there is a DC machine of large capacity, suppose 20 kilowatt DC machine, a DC motor or DC generator. Their armature current will be very large. If armature current is very large, there will be armature flux also very large, is not, and commutation will be further delayed, larger voltage will take place, will be induced in the quadrature axis. Whoever passes that zone, it will have additional induced voltage. In normal case, if I A is 0, nothing, no flashover, nothing, because I A is 0, no quadrature axis flux, everything is fine. But the moment large machines, large armature reaction, you cannot avoid this. Therefore, you must do something to avoid this armature reaction, and this I will discuss in my next lecture. So, qualitatively I have explained with simple logic, okay, these are the things going to happen and these are going to cause problems. Please understand that. Then we will actually draw the armature MMF diagram also, superimpose it with the field coil MMF and see ourselves, in fact it is happening. That is in the next class. Thank you.